Okay, so hello everybody. In this presentation, I'm going to talk robust and multi-objective optimal design of a racing car suspension system. So the focus here is on the racing car suspension system. So this work was conducted by Muhammad Ali Khan, Yousef Sardahi from Marshall University, and Carlos Castellanos. The outline of this presentation, I'm going to introduce the objective introduction, then I'm going to talk about the inerter because this is the hero in the case of the suspension system of racing cars. Then the methodology that we followed to design a robust and multi-objective optimal passive suspension system for racing cars, some of the results that we obtained, and some of the concluding remarks. So we are going to design a robust suspension system for a racing car. The design will be done in a multi-objective settings by considering three design objectives: the passenger head acceleration, the suspension deflection, and also the tire deflection. We are going to tune the coefficient of the sprung spring and damping. These are the spring constant and the damping attached to the body of the car. The tire stiffness in addition to the inertance of the inerter. This is the constant of the inerter. We are going to call it the inertance for better performance. Now, when we do the optimization, we are going to take into account also the variation in these four parameters during the optimization, because we know that during the operation of the suspension system, they will change and they will impact the passive suspension system in the car. So active suspension system were last seen in racing cars. Maybe they are common in passenger cars, but they are not common in racing cars, such as Formula One in 1993 and blocked after that. So in almost all, to the best of our knowledge, in racing cars, they use a passive suspension system instead of active suspension system. And there is a reason for that, because they are highly reliable, they are very simple, and because of their low cost compared to the other types. A new device called inerter were introduced to the suspension system of racing cars in 2002. In 2002, with the motivation to improve the mechanical grip of racing cars. Studies have shown that inertance, by adding the inertance to the suspension system, can significantly improve ride comfort, which is very important for racing cars drivers. Tire grip, okay, which is highly important in the case of racing cars, and handling, and also handling in comparison to the standard passive suspension system that only includes springs and dampers. Now, the concept of inerter was introduced in 2002 by Smith. He was trying to find a device that is similar to the ungrounded capacitor by using the analogy between mechanical and electrical components, and he came up with this device. So this is the one port, two terminal inerter that can be constructed by meshing a nut, screw, bearing, gear, and a flywheel. And the flywheel rotates proportional to the relative displacement between the two ports, or between the two terminals, I mean. And the dynamic of the inerters, the inerter is given by this equation. It's not clear here, I don't know why. It's F equal B, which is the inerter constant, multiplied by phi2 minus phi1. So this is the dynamic of the inerter. So soon after the inerter was introduced, it was first implemented in Formula One car in 2002. And Kimi Räikkönen used this car that implemented the inerter in the race of 2005, and he won the race. And I don't know why, maybe because of the inerter, or maybe he is a good driver. That was one of the secrets of Formula One, using inerter suspension and the other cars. And maybe that one of the reasons that contributed why they won the race. So we need a mathematical model in order to do a computer simulation. So here we use a quarter core model. The driver of the car is divided into the body, in addition to the seat, is divided into two parts, MT and MB. So the passenger and the seat is modeled by 2 degree of freedom system. Each is modeled by second order differential equation. The body of the car and the tire, they are also modeled by MS and MU by a 2 degree of freedom system modeled by second order differential equation. So we take the model of the car, and B in this case is the inertance. If you compare it with semi-active suspension system passenger cars, you can notice instead of B, they are using damping force. Here we are using just an inerter, which is simply a mechanical device that helps a lot in reducing the oscillation in the car body, or taking away the oscillation from the car body and improving the passive suspension system and the car performance. So when we do the multi-objective optimization, we need to include more than one objective: the mean effective value of the suspension deflection, the tire deflection, and also the head acceleration. The mean effective values are calculated according to this equation, which simply says that you take the design parameters, which consist of these four design parameters: KS, CS, B, and KY, and then we perturb them in the neighborhood of delta. Delta are the uncertainties which are given by these equations here, okay? And then we calculate the RMS for each objective, the RMS of DT, the RMS of DS, and the RMS of EH by doing a function evaluation at Y. Y is within the neighborhood of K by perturbing the design parameters according to the uncertainties or the variation of the design parameter, because as I said, we want to consider that in the optimization. We formulate the design objective, design parameters, the uncertainties, and also we define the constraints, and then we solve the problem by using non-dominating sorting genetic algorithm, which is one of the popular algorithms. We solve it, and then when we solve it, we actually do two things. We compare how the global solution will look like without considering the variation, which is in our case, these black stars, they represent the global solution without considering the variation. And then the robust solution by considering the variation in the design parameters, which are these blue dots here. The yellow region represents the feasible solution. So it's very interesting here to see that there is a conflict between the tire deflection and the suspension deflection. There is also conflict between the head acceleration and the suspension deflection. And we can notice that the robust solutions in this case avoids the boundaries of the feasible region, not like the global solution. Okay, so we take this and then say, okay, let's study the impact of the perturbation on the global and also on the robust solution. But we believe that the robust solution will be better, but we wanted to test that. So here we show the profile of the absolute deviation in the suspension travel, and also in the tire travel, and also in the head acceleration, okay, for the perturbed and non-perturbed global and robust solutions. So we take the robust solution and also the global one. The global solutions, it's like you are solving the multi-objective optimization without considering the variation in the design parameter. We want to see which one actually is more robust. You can notice that the blue one, even though it witness an increase at the beginning, it decreases very quick. This is the robust solution compared to the black one in all cases, which actually proves that the robust multi-objective optimization is working very well, and it's actually robust to the perturbation. And we expect if we implement this for a passive suspension system, it will give us better result. So we have studied the robust multi-objective optimal design of a passive suspension system with an inerter device. The optimization has only 4 design parameters and 3 objectives by one of the popular multi-objective optimization algorithm, non-dominating sorting genetic algorithm. The global and robust Pareto front were obtained. The Pareto set includes multiple design options from which the decision maker can choose to implement. Numerical solution shows that the robust multi-objective design is very effective and guarantees a robust behavior as compared to that of the classical multi-objective design. The result also show that the robust region is inside the feasible objective space and avoids all of its boundaries. If we go back to the Pareto front, we can simply notice that. Thank you very much, and I welcome your questions.